Hello and welcome to this video on nucleophilic addition. My name is Ochem, and in this video we'll be predicting the products of a Wittig reaction, or the conversion of carbonyls into alkenes. Wittig reactions are an interesting subtype of nucleophilic addition reactions, where the carbonyl oxygen and aldehydes and ketones are replaced by a double bond to carbon, forming an alkene. This is accomplished through a Wittig, which is a type of Zwitter ion where the net charge of the molecule is zero, but there is a negatively charged atom covalently bound to a positively charged heteroatom. The negatively charged atom is often carbon, making it a great nucleophile. The positively charged atom is often nitrogen, sulfur, or phosphorus. The most common Wittig used in the Wittig reaction is a phosphorane, where 3 phenyl groups are attached to a phosphorus atom, which is covalently bound to an alkyl group through a double bond. Phosphoranes undergo resonance so that the phosphorus has a positive charge and the carbon has negative charge. Notice the net charge is 0 and that the 2 atoms bearing charges are different, fulfilling the Wittig criteria. The Wittig reaction occurs in 2 steps. First, the nucleophilic carbon will attack the carbonyl carbon, and at the same time, the double bond in the carbonyl will attack the positively charged phosphorus to form a 4-membered cyclic intermediate called an oxphosphatiene. Next, a fast decomposition step where double bonds are formed will result in an alkene and triphenylphosphine oxide. The overall reaction is essentially replacing the double bonded oxygen with a double bonded alkyl group from the phosphorane. Let's see some examples of how Wittig reactions look by predicting the products of the following reactions. In A, we have methylene triphenylphosphorane, which undergoes resonance to have the formal negative charge on the alkyl carbon. The shortcut would be to just sub in the methyl group in the phosphorane for the carbonyl oxygen on acetone to create 2-methylprop-1-ene. However, let's make sure by drawing out the mechanism. The nucleophilic carbon will attack the carbonyl carbon to produce a 4-membered cyclic oxaphosphatane intermediate. Decomposition yields the triphenylphosphine oxide and our product 2-methylprop-1-ene. Since this is a nucleophilic addition reaction, let's quickly double check to make sure all carbons are accounted for. 1 carbon in the Wittig plus 1, 2, 3 carbons in acetone should give us 1, 2, 3, 4 carbons in our product with a carbon-carbon double bond. The Wittig in this reaction is ethylene triphenylphosphorane, undergoing resonance to create the negative charge on the alkyl group. Again, the shortcut here would be to sub in the alkyl group for the oxygen in butanal to create the product hex-2-ene. The mechanism, just like many of the nucleophilic reactions we've recently seen, is the nucleophilic carbon will attack the carbonyl carbon to produce the oxaphosphatine cyclic intermediate. Quick collapse of the intermediate to eliminate triphenylphosphine oxide gives us a product hex-2-ene. Quick double check. 2 carbons in the Wittig plus 1, 2, 3, 4 carbons in butanal creates 1, 2, 3, 4, 5, 6 carbons in the product with a carbon-carbon double bond. Don't let the new and strange words in Wittig reactions throw you off. This is a familiar reaction. The nucleophilic carbon in the reagent will attack the electrophilic carbon to create a new carbon-carbon bond. Only this time, instead of reducing the oxygen to an alcohol, we're eliminating it entirely and adding in an alkyl group at the same time. Great job working through this lesson.